Yeah, we're not brother stuff. Yeah.
Oh yeah, no. My brother doesn't hit legs, so these are kind of just like those. It's not bad.
I mean, like, it makes sense. Oh, yeah, I had to dig through my brother's. I was like, oh, like, I guess I was like, you figure out where these.
Or you can.
Like it's literally I push something. Like it wouldn't be there.
Yeah.
Okay, guys, turn to page 19.
Me too. I think it's only that. I know, I was confused. Yeah, but like, there's different ones that things are trying to figure out. Population and that was like, this thing. When we went to like, those actually, like doing them. I did it like 20 times. I couldn't see this thing. But then I going to like, there's the one that was like, here's the like 300, 200, 400. Oh my God. I bet 400 was.
I like tried both equations. Like they were good.
And I didn't get the exact number, but it's not like close to 4K. So I was like, I got like 4 low and like a low. I was like,
Yeah.
That obviously.
Possible parts of that. You know, the teacher. All of them.
Okay, so page 19.
Last questions really still narratives. Like drop. Chances are because we have basic steps.
I'm so tired of class. The new graduate, I'm learning.
It's an only rabbit. Or we might think like speak rabbit on stuff like that.
Okay, so you'll see a problem like this on your test. The optimization problem will be similar to this, where you have a rectangular container and you have to involve cost and surface area and volume. So, okay, let's read this problem here. Rectangular storage container with an open top. So open top, there's nothing that is closing this in. Well, there's only 5 sides for this that we have to worry about. There's a volume of 10 cubic meters. The length of its base is twice its width. Material for the base costs $10 per square meters. Material for the sides costs $6 per square meters. Find the cost for the cheapest container. Okay, so there's a relationship between the length and the width. So if I call one side X, I can call the other side Y. 2X, yeah. They don't provide any relationship between the height and the base and the width length. So we have to use different variables. So we can use H or we can use Y. I'm going to use H. Okay. Find the cost of the material for the cheapest container. So cheapest container, we're paying for the material that makes up the box, not the space inside the box. So we're going, so you know the cost is going to be associated with surface area. Right, let's build surface area and then we can work in the cost. So this is not something that I want you to memorize. I just want you to kind of build it step by step, right? There's 5 rectangular surfaces, and you're just going to be adding up the areas of each of those surfaces, and that's your surface area. Okay, so let's start with the base here. What's the area of that base? Yeah, 2x times x, which is 2x squared. So now the remaining sides are the vertical facing, are the vertical sides. Let's do this larger side first here, the front facing side. What's the area of this side? Yeah, 2x times h, good. And if there's a 2xh in the front, there must be a 2xh in the back. And then what about the side, the more narrow vertical side? This has an area of what? xh, okay. And if I have an xh on one side, there must be another xh on the other side. So we have 5 surfaces, 1, 2, 3, 4, 5. We're just doing areas of each of those 5 sides. Okay, good so far? Okay, so we're paying for the surface area, right? We're paying for the cost is going to come from the material that makes up the size of the box. So we have $10 per square meters for the base. So we know we can multiply $10 into that component. And then the $6 is for the rest. So everything else is times 6. So I can also update this surface area variable to call that the cost equation now. And now, ultimately, I'm going to be putting a star next to this. I want to find the derivative for this cost once this is ready. Okay, so multiply this through 20x squared plus 4, 5, 6. This is 6xh times 6. Okay, so we want to find the derivative, but there's one variable that's sticking out that we have to, we need some support from another equation. And so the other equation is going to come from your volume. So what's the volume for this box based off of the variables that we have established? Good. Length times width times height. So 2x times x times h. So 2x squared times h. Now we do have some restriction, right? The volume of the box has to be what? 10. Okay. Let's solve for h. And once we can solve for h, we can replace the h in terms of x. We can get this cost equation ready for power rule, find the derivative, find a critical point, and then that's basically where our answer is gonna be. So we're getting closer to being ready to do power rule. We do have to clean this up, make sure our variables are in the numerator, and then once everything is ready, we can find C prime, set C prime equal to 0, find your critical point. And then once we find our critical point, we just go back and reread the problem and make sure that we're providing the information that they're asking for. Right, I do want to make sure that X is up at the top, so I don't have to go through quotient rule. I can just go through power rule once that X is up. Okay, set C prime equal to 0 and begin looking for your critical point. I put that over 1, I can cross multiply. Take the cube root. Or you can enter this in as 9 over 2 raised to the 1/3. Either way. Okay, we'll get a decimal version of that critical point, 1.651. And once you find your critical point, you should be near the end of your problem, but we don't want to just assume this is going to be the answer because it says, it may be asking for the cost, it may ask you for the dimensions. But the good thing is that once you solve for X, all you're doing is you're just putting back into one of the equations that's been established. You should not have to create any more additional data or any more additional formula. Every formula that you need should be ready for you to plug in and find. So find the cost of the material. So I want to plug this into one of the cost equations. There's multiple ones. You can put it into the original one, or you can put it into the one that's involving just X, but just make sure you don't put it into C prime. But any of these cost equations will get you the same answer. But if it's asking for dimensions, then I need the width, the length, and the height. So if I want to find the length, I can just multiply 2 by 1.651. If I want to find the height, there's my height formula, 5 over x squared. All right, any questions here? Okay, just real quick here, if you turn to the very back of the packet, this is what your test will look like on Friday. You're going to see a derivative graph, just like how we did on page I'll put down the page 3 and page 7. You'll see an optimization problem, just like what we did on page 19. There'll be a curve sketching problem, like number 1, like page 1 and page 8, like we did for homework. And the rest of the questions will just be related to topics from 5153 quiz. So extreme value theorem, mean value theorem, roles, first order test, second order test, test for concavity. Okay, so this is what your test will look like. Right, so should be no surprises. If you feel good about these practice problems that we've been doing, you feel like you can solve these problems from scratch, you should just get the same type of problem, just with different numbers. All right, let's go to page 11 and let's review some of the 5153 quiz topics. Okay, page 11, let's look at number 3 here. Okay, so here's some review. This is with Rolle's theorem. And I'll put in parentheses mean value theorem, because Rolle's theorem and mean value theorem are essentially the same. Here's the formula here. You're going to find your endpoints, find the slope between the endpoints, and then you'll set that number aside. That's going to be your slope value that you're trying to guarantee. And then separately, you're going to find the derivative. And then in the end, you're just setting them equal to each other and solving for x. So number 3, verify that Rolle's theorem applies and find all the numbers that satisfy f prime of c is equal to 0. Okay, so let's go from the beginning here. Between 0 and 4. All right, what conditions come along with Rolle's theorem and mean value theorem? Function needs to be what? F of x needs to be continuous. And what notations do we use for continuity? Brackets, yeah. Continuities with brackets. And then differentiable is with what? Parentheses, yeah. Okay, and then these two conditions are just for Rolle's theorem and mean value theorem. For extreme value theorem, it's only continuity. So I think I indicated on your quiz, if you included differentiability on extreme value theorem, it may be true in the sense that the function may pass the differentiable test, but it doesn't need to. So with the extreme value theorem, we just use continuity. We just require continuity, but then for mean and Rolle's theorem, we need continuity and differentiability. All right, so with Rolle's theorem, let's go ahead and confirm what our order pairs are, and then we can find the slope. But with Rolle's theorem, the slope just has to be 0. But mean value theorem, the slope can be anything, including 0. Okay. But Rolle's theorem is very specific, it needs to be 0. So let's go ahead and find the order pairs here. 48 minus 48 is 0. 0 plus 1 is 1. So my order pair is 0, 1 and 4, 1. This should give me a slope 0 because the y values are the same, but let's confirm. So changing y over changing x. 1 minus 1 over 4 minus 0 is 0 over 4, which is 0. Okay, so we know Rolle's theorem can be applied because the two order pairs are directly across from each other. If I draw a line between those 2 points, it's going to be a horizontal line, and that horizontal line is a slope 0. All right, next up, derivative. So we took care of this part, right? We know what we're trying to target. We're trying to target a slope of 0, and we're just going to find f prime. So basically, Rolle's theorem is going to feel like you're just finding critical point. Okay, we're just finding critical point, but we just have to go through this additional verification that there is going to be a slope 0 before we find that critical point. But yeah, basically, Rolle's theorem is finding critical point, setting f prime equal to 0, but it just requires this additional check. Okay, I have my slope formula. I'm now asking the derivative to tell me where is there a slope 0 on the curve. Solve for x. So c equals 2. Okay, any questions? All right, number 4. Let me read the problem here. Number 4 says, which of the following statements is true about the function x to the 2/3? Now, if you look at your answer choices, there's information about f prime. There's information about concavity. So let's go ahead and just build everything we can from this function. Let's create our slope sign line. Let's create our concavity sign line. Let's have everything in front of us, and then we should be able to check off to see which ones apply. Okay. So I'm just going to treat this like a curve sketching problem and build everything about the first and the second derivative. Okay, power rule. Let's do some cleanup here. So if I have my derivative, where do I look for critical points in general? Numerator and denominator, right? Doesn't mean that you're going to find in both locations every time, but we have to make sure we look in both places. Anything from the numerator? Right. If I set 2 equal to 0, there's nothing to find. But if I set 3x to the 1/3 equal to 0, what's my critical point there? Divide by 3, cube both sides, x equals what? 0. Yeah. So there's one critical point. Let me just create a sign line in case I need it. If I plug -1 into the derivative, 2 over 3 times cube root of 1, cube root of -1, that's going to give me a negative decreasing slope. If I plug 1 in, I'll get a positive slope. So negative slope, positive slope, we expect a relative minimum, right? Okay. F double prime. I'm going to pick up where I left off with this f prime. I prefer to find f double prime with this version than this version because this is ready for power rule, but this I got to go through quotient rule. So I'm going to go through this. Power rule. Okay, bring down the exponent, subtract 1 from the exponent. Negative 1/3 minus 3/3 is negative 4/3. Okay. Again, I look for critical points in the numerator and denominator, and the only one I'm going to find is what? X, yeah, denominator. Set that equal to 0. I'll also get what? 0. Yeah. Let's check for concavity here. So plug negative 1 into my second derivative. Now this is raised to the 4th power, so that's basically going to force everything here to be positive, no matter what I put in for x. So denominator is always positive, my numerator is always negative. Negative over positive is negative. If I plug 1 in, I'll also get negative. So if you plug this in the calculator, this is what the graph could look like. Also, if you look at that 0 there, that 0 is coming from the denominator of f prime. 0 will cause my slope to be undefined, right? So that means this is going to be a sharp turn. So imagine what a sharp turn could look like. The graph is decreasing, followed by increasing. There's a sharp turn here. It's concave down, followed by a concave down. So the graph's going to end up looking something like this. Okay, so now to answer the questions, there's a critical point at 0, 0. That's option 1. So if I plug 0 into the original function, I do have a critical point. The order pair is 0, 0 because if I want to find the y value, I can insert 0 into the function. So 1 is true. F prime of 0 and F double prime of 0 are both undefined. That is true. If I plug 0 in for F prime, I'll get 2 over 0. That's undefined. If I plug 0 into F double prime, I'll get negative 2 over 0. That's also undefined. So they're critical points because they're coming from the denominator, but they're also causing the slope and concavity to be undefined because of that sharp turn. Okay, so 1 and 2 are both true. Curve is concave up from 0 to infinity. That is false, right? Everything we see is concave down. And then the curve is concave down from negative infinity to 0. That's true. So everything is true except for 3. So 1, 2, and 4. Right, let's do a second derivative graph like how we see above on page 11. Okay, so second derivative graph has zeros at x equals a and x equals c. The function, when is the function concave up? So we know if we're looking at the second derivative graph, our y-axis represents concavity. So anything above is concave up, anything below is concave down, anything on the x-axis is point of inflection. Right? We don't want to look at this and say, oh, everything's concave down because of the shape. This is not the original function. This is f double prime. So vertical points, x-intercepts, that's going to be A and C. Sorry about these typos there. It should be x is less than A, x is less than B, x is greater than B, x is less than A, or x is greater than C. So ignore the the zeros in front. All right, what behavior are we expecting to the left of A? This is what? Yep, because this is our guide, right? Okay, concave up. Between A and C, concave down. To the right of C, concave up. So our graph is concave up, and these two intervals to the left of C and, sorry, to the left of A and to the right of C. Okay, page 12. There's a problem here that's on the side. This is going to be number 6. This is mean value theorem, sorry. Okay, I'll put this on a separate sheet. So well, they're setting us up for mean value theorem. It says find the average velocity during the first 4 seconds. So basically, mean value theorem is this, but we can adapt it in terms of particle motion. All right, so instead of f and f prime, we can think in terms of x and x prime, x being position, x prime being velocity. So we're going to find the average rate of change, or in this case, average velocity, and then set equal to the velocity function. So we have our x of t here. And then our interval is from 0 to 4. So we're just applying mean value theorem. So find the slope between the endpoints. The slope between the endpoints is your average velocity. So we'll find x of 4, find x of 0, x of 4 minus x of 0 over 4 minus 0. But just as a reminder, this is mean value theorem. So our conditions do pass. Continuity on the closed interval, differentiable on the open. Yeah, so find the average velocity. That's going to be the left side of mean value theorem. And then use mean value theorem to confirm that at some point, first 4 seconds, the instantaneous velocity equals the average velocity. So anytime you see the average rate of change equal the instantaneous rate of change, that's basically the problem indicating that they want you to apply mean value theorem. So there's my average velocity. You can find the derivative, which is going to be velocity function, x prime, or V of t. So this is my average velocity portion. This is my instantaneous rate of change portion. And I'm just setting these equal to each other. And the final part is basically asking for the order pair. Find the time and the height. So I have the time and the height is related to the position function. So I can just find the height by plugging 2 into the position function. Okay, so the big picture here is between 0 and 4 seconds, the average velocity is negative 19.6 meters per second. And we know that if this is the average velocity, this object is going to have to hit this velocity, exact velocity at some moment in time. And so the question is, when is it going to hit this exact average velocity? And it's going to hit it at 2 seconds at a height of 480.4 feet. So at this moment in time is when this object is going to reach this exact velocity. Let me see. Okay, page 16. We're going to skip these problems on page 16, but I want to highlight a problem from your quiz that I want you to be able to do. And this is involving second derivative test. So let's say I had an order pair, 3, 6. My slope at that point is 0. And my concavity at that point is 25. What can we conclude about this point? This is basically application of second derivative test. And some students were a little bit lost with this problem on the quiz. They would say, oh, there's a relative max at 3, 6. There's a relative minimum at 3.25. This is all talking about the same point. So the idea is that if we can verbalize what's happening, it's all describing the same location, but just different pieces of information about that location. So this is talking about the order pair, the physical location, right? This is talking about the slope behavior, right? At this point, there's a slope of what? Slope is 0. And then at the same point, the curvature is going to be what? Concave up. So if we combine all this knowledge into the same point, we should be able to create a picture that looks like this. Okay? We know the physical location. We know the slope. It's got to be a flat surface, and it's got to be concave up. So the only way that we can create a graph that has all those 3 behaviors is if it looks like this, right? Again, this number doesn't mean anything. It just means the only thing we care about is the fact that it's positive. Concave up, slope 0, or the physical location is 3, 6. We must be looking at a what? relative minimum. Okay, and then we're going to skip number 4, but I want us to do a real quick practice problem on extreme value theorem. So the instructions here is find the absolute max, absolute min. So I think on the quiz, some students were trying to do a first order test. They're trying to do relative min, relative max. Now with extreme value theorem, all you're doing is you're finding critical points, and then you're testing your critical points and your endpoints back into the original function, and you're just comparing the y values. Okay, we're not, there's no sign lines involved. It is just critical points and endpoints into the original function. Okay, so extreme value theorem, we're just trying to find the max and mins, find the absolute max and min. First thing is we have to establish the condition. There's only one condition for extreme value theorem, and what's that? Continuous, yeah. Okay, next up, find your critical points. Set equal to 0. Find your critical points, x equals 1 and x equals 3. But are we going to always test every critical point that we see? Where does it have to be? Yeah, it has to be in the interval, right? So something is not inside the interval. Which one are we going to not use? 3, right? So 3 is out. Now, they all go back into the original function. Now we're just finding the physical locations at these points. So we have to plug 1 in, plug -1 in, plug 2 in. And compare the y values. F of 1 is 4, f of -1 is -16, f of 2 is 2. And for extreme value theorem, I only want the y values. So absolute max is 4, and absolute min is -16. Okay, so I just want to make sure I review extreme value theorem. Some students were plugging these into the derivative, or forgetting the conditions, or including all the critical points, or just testing critical points but not endpoints, or giving me the x and y values. So in all these things, that can impact things. Okay, so your homework tonight, it's just going to be 1 page. It'll just be page, and I'll send out a reminder this afternoon. Just page 15. Page 15. All right, come get your phones.
I'm just looking at my quiz and I was confused why I got counted off for being outside of the limit.
Right,
thought there was
so
a
for mean value theorem, it needs to be inside the interval.
Okay.
So it needs to follow this rule of differential. So that's why I took it.
Okay.
Yeah, thank you.
Is it, do you use brackets for critical points?
I'll use parentheses for everything.
Oh, okay. So whenever I get this kind of problem, I would always.
Yeah, just always.
Substitute.